Stepping out into the universe, we must confront the reality of interstellar travel. We must reach far beyond our own lifespans. We must think not as individuals, but as a species.
J.R.R. Tolkien, author of the Lord of the Rings saga, developed arguably the richest example of world-building in human literature. In his tales, the elves are the firstborn upon Middle-earth, blessed with sagacity, guile, and skill in many forms. The elves love their Middle-earth, but something gnaws at them. Over countless centuries, they feel a growing urge, a so-called sea longing. The ocean calls to them. And no matter how hard they try, it's always there, compelling them to leave Middle-earth, and that their fate lies across the distant horizon, to another world, a land of bliss and majesty. I think that the same is true for us, that we too are compelled to look out to distant shores, that we too feel a sea longing, an urge to visit other worlds, to run our fingers through the sand of alien beaches. Look, at the end of the day, humanity has two choices, two distinct fates that lie ahead of us. Choice one, the earth is our cradle and it's our tomb. Our story ends here, just how it began. Should other civilizations be out there amongst the stars, then they never end up noticing us, and quite frankly, we may as well have not even existed as long as the galaxy was concerned. Or there's choice two. Maybe, just maybe, we choose to leave. Humanity spreads across the dazzling sky, discovering countless globes, expanding our knowledge to unimaginable extent, perhaps even representing the spark which awoke the cosmos. The journey from here could be beyond anyone's wildest imagination.
This world was never enough for you, was it, Coop?
What, 'cause heading out there is what I feel like I was born to do? Mankind was born on Earth. It was never meant to die here.
Now, I can't speak for you or for anyone else, but for me, the choice has always been clear. Ever since I was a boy, I have felt that sea longing. I have spent countless hours looking up at the night sky and dreaming of ways to reach those stars. As a child, I'd fantasize that the Starship Enterprise would sweep across the sky, beam me up from my backyard, and let me share upon their trek across the stars. But as that fantasy subsided and I grew older, I became fascinated by the real-world prospect of warp drives and wormholes. Maybe we could invent the dream out of pure force of will. Encouragingly, in 1996, NASA founded the Breakthrough Propulsion Physics Project to investigate these radical ideas, and when I learned about that, it gave me profound hope, for someone else was out there who shared my dream. But when I was 17 years old, that project was shut down. Another hope snatched away, another door closed.
Well, we used to look up in the sky and wonder at our place in the stars. Now we just look down and worry about our place in the dirt.
15 years after that project ended, the spark renewed. Silicon Valley billionaire Yuri Milner audaciously invited a group of physicists to his home to tackle the problem. His question was blunt. Given our existing technology and the known laws of physics, is there any way at all that we could plausibly send a probe to another star system in our lifetime? The crack team, including Sir Martin Rees, Freeman Dyson, and Stephen Hawking, converged on a solution, their best bet, a laser-propelled light sail.
Let's talk about this. This is interesting.
Well, there's a just tremendously exciting prospect called solar sailing.
Solar sailing.
And this is a very crude model, and which travels on the radiation and particles that come out of the sun, the wind from the sun. And because it has a constant acceleration, it can get you around the inner part of the solar system a lot faster and a lot more conveniently than the usual sorts of rocket propulsion.
So this is conceptually similar to a solar sail, which could be, for example, a large thin sheet of aluminium that is gently accelerated under solar radiation pressure. But the problem is, that's just too slow to reach another star, so they juice the sail by firing 100 gigawatt lasers at the thing. Even then, the probe needs to be incredibly light to reach that target speed of 20% the speed of light. So the team designed a tiny microchip sat, similar to that found inside your smartphone, that would be woven into the fabric of the sail itself. Milner announced the concept in 2016 to media fanfare and dubbed it the Breakthrough Starshot project, backing it with $100 million of his own money, and we did a video about that at the time. So, almost a decade later, where are we at? Well, the project was inspirational, but in many ways it was also aspirational, because the truth is that a slew of engineering problems make such a vision impractical, and many now doubt they will ever come to pass. So, one of my favorite science communicators, the wonderful person Anton Pedrov, has a great video summing this up, and I'm going to direct you to that to learn all about it. Amongst the many problems here is that building 100 gigawatts worth of lasers powered by enormous nuclear power plants presumably is going to be expensive. And remember, we're living through an era where NASA science funding is being gutted, the US national debt is becoming untenable, and heightened tensions between superpowers make it difficult to propose building what is effectively a superweapon. And so, just like with the other cases, my dreams of interstellar travel are squashed by practicalities, by funding priorities. At a certain point in your life, you realize that you're running out of time, that no one is going to come along and solve this for you, that the cavalry ain't coming. You're going to have to roll up your sleeves, put your big boy pants on, and try. And you might fail. In fact, you probably will fail. But this is it. This is your life. No one's got your back. And if you don't do this, it probably won't happen. And look, let's be real here. I'm no genius. I'm not Sir Martin Rees. I'm not Stephen Hawking. And hell, I certainly wasn't invited to Milner's crack team of brilliant physicists. But look, at the end of the day, I just simply don't have time to wait for the next Einstein to solve this for me. And to be clear, I do not expect that my ideas are going to solve interstellar flight. I'm not that arrogant, but maybe it might flesh out some of the possibilities. Maybe it might add another option to the menu, and perhaps it might even inspire some of you watching this right now to try as well. So here is my attempt.
How's your mathematics? Not good enough for the physicist he wants to be.
Algebra's like sheet music. The important thing isn't can you read music, it's can you hear it. Can you hear the music, Robert?
Yes, I can.
Starshot is a great solution if you have a bottomless pit of money. You know, personally, the whole Starshot concept reminded me a lot of the solar lens telescope concept. Fly a spacecraft out to about 1,000 AU from the sun, so that's about 25 times further out than Pluto, and light from distant stars will gravitationally lens around the sun to a focus. This has long been recognized as representing essentially the ultimate telescope imaginable. Such a device would effectively be a sun-sized telescope, capable of imaging surface features on nearby exoplanets. But the problem is again cost. Yes, this is a great solution, but 1,000 AU is extremely inaccessible. It's not just a question of getting there, but also stopping in the correct orbit, having a large enough antenna to beam the data back to Earth, having a sufficiently large power system that can last for probably decades, maybe even a century to power that thing, and all of this operating for probably, again, like a century for this to financially make sense. So in 2019, I suggested a cheaper knockoff version. Forget the sun, use the Earth. Now yes, the Earth doesn't have enough gravity for this lensing, so instead, let's use its atmosphere, refractive lensing. Dubbed the Terrascope, the capabilities are far more modest than a solar lens, but still provide amplifications of over 22,000 for a 1 meter sized telescope. So that effectively turns your 1 meter sized space telescope into a 150 meter sized one. And there's no need to fly to 1000 AU here, this is all possible in Earth orbit. And so maybe that's my expertise, to think of cheaper, scaled down versions of our mega engineering dreams. And so when it started to become clear that Breakthrough Starshot was running into obstacles, I started to wonder, could there be a cheaper way of going interstellar? And yes, maybe we won't reach 20% the speed of light anymore, but maybe there's a way. Maybe there's a way to twist the concept into something more feasible, yet still useful.
Come on, Tars. Come on, Tars.
We all know the Interstellar meme, certainly on this channel you should. The incredible docking scene shows the terrifying effects of centrifugal forces on the crew, causing Dr. Brand to black out and almost doing the same to trained pilot Cooper. It's the kind of haunting scene that sticks with you long after leaving the movie theater, and for me, that influence was inspirational, because like a flywheel, the Endurance has amassed an enormous amount of rotational kinetic energy, and therein lies the key. Okay, let's take a step back and just look at solar sails for a moment. You don't necessarily need to replace the sun with expensive giant lasers, because even at 1 AU from the sun, we receive a respectable 1.38 kilowatts per meter squared. Now, if that power could be held constant, you could accelerate a Starshot-like sail to 10% the speed of light in 20 years using just the sun. So power isn't the problem. The real problem with a solar sail is that it just won't stay put. Because if you start off with a motionless sail facing the sun, it will gradually accelerate under radiation pressure, and of course that acceleration is always directed away from the sun. And therein lies the problem. As the sail accelerates away from the sun, increasing its separation, the radiation pressure drops off as 1 over distance squared. And so what this means is that even in infinite time, the sail can never reach even 0.04% the speed of light. If only there was a way to somehow trap all of that solar energy at 1 AU distance, somehow charge up some kind of giant battery and then release it all at once. Now, a flywheel is a battery, a mechanical battery. Not only does your car probably have one, but NASA have experimented with high-performance versions like the G2 wheel that could hold 1.89 megajoules of energy. Here, we finally come to the simplest version of what I'm proposing in my new paper, which was published earlier this year. Imagine 2 thin and same-size sheets of material in space, both facing the sun. Now, we're going to have one of these sides be silver and the other be dark, and we're going to orient them such that they have opposite phases to one another, and finally we're going to connect them together with a tether. Now, if we put such a thing in orbit of the sun, it will feel 2 sets of radiative forces. First, both paddles here will feel an outward radiation force, but the silver-facing side will feel about twice the amount of force. As a result, the entire system will start to spin, and it will continuously accelerate in this spinning motion. That's our flywheel, our battery storage system. Now, this might look familiar to some of you. It's essentially a radiometer in space. That's a simple toy like this one, where a light shined on the paddles induces spinning. However, with this toy, it actually ends up spinning the wrong way because the paddles heat up and interact with the surrounding air, causing air currents that drive it the wrong direction. But there's a problem with this idea. Because both paddles feel a net outward force, then the entire system should be pushed outward. If left in inertial space, the thing would indeed accelerate away from the sun, just like a solar sail. So we need to stop this from happening. So this is where threads of your life kind of come together in unexpected ways. Because you see, in 2019, I came up with, I guess what you might call another little invention, which I called the quasite. Now, the quasite is a twist on another concept, which is known as the statite. So first, let me explain that. A statite is a solar sail that is so thin and shiny that the outward radiation pressure caused by the sun perfectly balances the inward gravitational pull. In this way, statites can just hang out there in inertial space and be perfectly stable. Now, of course, planets are also stable around the sun, but for a very different reason. Orbits. You see, a planet is in fact always falling towards the sun, but it just so happens that its tangential velocity is sufficient to maintain the same altitude around the sun at all times. That is an orbit, or really in that case, a circular orbit. By the way, if you are digging this new cool t-shirt I'm wearing, this is a newly commissioned piece that we've had made for us, so please do check it out using the store. That's the shelf down below, so you can grab it for yourself. Okay, so a quasite actually blends these two stability methods together. It is thin and shiny, but not enough to resist the sun's gravity completely. It's not a statite. As a result, it needs a modest amount of tangential velocity in order to resist infall. In this way, quasites are again stable, but they seem to orbit the sun at an eerily slow speed, slower than Kepler's laws would predict. Now, when I first came up with this concept, it really wasn't obvious what this thing would be used for, but hey, I didn't really care. I just enjoyed the math of it. But 6 years later, quasites come in and save the day, because now our giant spinning system becomes a quasite. Yes, it feels an outward radiation force, but that doesn't exceed gravity, so the thing remains stable as long as we nudge it with the appropriate tangential velocity. In other words, we put it into a quasite orbit. So, how does this spinning mess end up giving us interstellar travel, you might wonder? Well, the final piece of the puzzle is to metaphorically nip into Breakthrough Starshot's labs and steal their concept of the microchip sat and simply stick it onto the end of our spinning system. As the system spins up, getting faster and faster, it will eventually reach a critical speed where the centrifugal force becomes too much. Whereas in Interstellar, this causes Dr. Brand to black out, here it causes the tether to snap. And just before we reach this critical velocity, we release the microchip sat. It thus flies off at high velocity into deep space at interstellar speeds. So we need a name. Now, I'll confess, I spent way too long thinking about this, thinking about names like the solar catapult or the slingshot or something, but as I'll argue later, this thing could be used for much more than just interstellar travel, so those names felt a little bit too constraining. Now, given the inspiration of this thing behind Interstellar, there was one name that stuck out in my mind.
Cars. 72 hours, yeah?
Roger that, Cooper.
TARS. Torqued accelerator using radiation from the sun. So we have a sci-fi film inspired by science that then itself inspired new science. This is why we need the arts. And at the end of the day, hey, I'm a sci-fi nerd. I should get to be able to call my crazy inventions whatever the hell I want. So at this point, I had the basic idea and worked out the math, but this tether system seemed a little bit wasteful. After all, the tether is just dead weight. It doesn't actually help harvest any solar energy. What if we extended the sails all the way across, so the tether now becomes part of the sail, forming a ribbon? Okay, great, but surely there should be some kind of optimal shape to this ribbon, right? So this is where we get a bit more into the engineering design of things, which is just simply not my expertise. I mean, I was trained as a physicist and not as an engineer. So fortunately, thanks to the support of many of you who support my research team, I was able to hire an engineer to help with this, Catherine Lampo. She's a brilliant undergraduate working at Columbia University, and I was able to recruit her onto this project thanks to your donation. So that's why there's no sponsor on this video. It's because you guys made this happen. Together, Catherine and I played around with different designs and eventually converged on squishing our ribbon at the ends and stretching it out in the middle. This helps because the tension felt is greatest in the center, so here you want plenty of material to hold the thing together. The tension drops off towards the end so we can get away with less material there. In practice, we segmented the ribbon into finite chunks and balanced the forces at each intersection point, iteratively solving for the final shape. Smoothing it all out at high resolution, you get something like this. The shape might seem strange, being perhaps surprisingly wide in the middle, but this is actually a design requirement for stability. You see, the rotation axis runs along the center of TARS, and for stable rotation, we need that to be either the principal or minor inertial axis. If TARS gets too long, that rotation axis equals the intermediate axis, and once that happens, the whole thing is at risk of tumbling, also known as the T-handle effect. Here, you can see a neat example of this for a spinning bolt on board the International Space Station. We definitely don't want this happening to TARS. After all of these design considerations, the question then becomes, how fast could this thing actually go using realistic existing materials? In our paper, we presented one example calculation. Let's make TARS about 7 meters wide, 63 meters long, and just 2.8 microns thick. We considered carbon nanotube sheets to be the best material currently available thanks to its high tensile strength to weight ratio. You can even actually buy these on Amazon. We would then spray one side with about 10 nanometers of nanostructure silver to make it highly reflective, and the other side could use a film of carbon deposition. The total thickness of 2.8 micron should be sufficient for a modern computer chip to sit flush against the ends and could be up to 10 by 10 centimeters in size. The whole thing would weigh about 1.6 kilograms, so it would actually be very light to launch. One could imagine rolling up into a cylinder and then unfurling it in space like an accordion. I think during this process, you'd likely need to apply some initial thrusters or lasers to start the spinning motion and give you that initial rotational stability. In this configuration, TARS would gradually spin up over the course of 3 years until it finally reached its critical breakup speed of 12.1 kilometers per second, a limit set by the tensile strength of our carbon nanotube sheets. However, because of the quasite orbit, it would be moving around the Sun at 28.3 kilometers per second, a little slower than the Earth's 30 kilometers per second. As we approach the critical spin speed, TARS would release its payload chip, which would exit with a speed of 40.4 kilometers per second. This just exceeds the solar system's escape velocity of 40 kilometers per second, and thus our chip would indeed go interstellar.
Okay. And for our next trick.
So, in a few years, using only energy from the sun, no lasers involved, and existing materials, TARS could be a plausible launch system for low-cost, small interstellar probes. And really, there's no reason to launch just one probe. We explore in the paper the idea of sequentially launching multiple probes, and that would form a daisy chain of probes through space towards your destination, providing a relay network for data transmission. Now, I promised you a concept for interstellar travel, and whilst I did deliver you that, you might reasonably feel a little bit shortchanged here, because at the end of the day, these speeds are still way slower than the speed of light. I mean, we're talking more like the speeds of the Voyager 1 and 2 probes, but at way less cost. Now, I think personally that is still very valuable. We should probably think of interstellar travel as a multi-generational activity. However, I am also impatient, just like you. So let's ask the question, is there any way that we can take this concept and somehow speed it up even more? There's a few tricks we could try and play. For example, kicking TARS into an eccentric orbit and then releasing it at perihelion allows us to exploit the so-called Oberth effect for reduced charge times and higher terminal velocities. A more obvious change is for our material scientists to finally crack the manufacture of large sheets of high-grade graphene, which is many times stronger than carbon nanotube sheets. A third option is to steal some velocity from Jupiter or Saturn on the way out, just like the Voyager probes did using gravity assists. That might boost you another 10 kilometers per second or so. Fourth, it should be noted that the payload doesn't necessarily stop accelerating. It can be a solar sail and so steal a bit more speed on its way out too. So altogether, these tricks definitely do help. They will improve our final terminal velocity, but they are still a far cry from the kind of relativistic speeds that we would really want to be reaching. So I guess that's it then. I guess that is as far as we can push this TARS system. Oh, but there is just one more trick, one more strategy that maybe might just work. You know, the Earth's equator is spinning at about 0.5 kilometers per second. That's pretty fast, but people don't just fly off into space. Why? Because of gravity. There's a restoring force opposing the centrifugal force. What if we could play the same trick for TARS? Consider electrically charging one side of TARS positive and the other side negative. Now, you'd have to insulate the center, of course, but if this worked, the charges would create an electrical force resisting the centrifugal force. Who needs super strong graphene if you can artificially enhance the strength using electric forces? Now, the problem with this is that we have two electrical charges spinning around. In other words, a rotating dipole. And as any good physicist knows, and as Maxwell taught us, a rotating dipole will generate a magnetic field and radiate away electromagnetic radiation. So when the thing is spinning pretty slowly, the amount of energy being leaked out through this radiation is fairly small. It's not a big deal. But as TARS spins faster and faster, that leakage becomes quite profound. In our paper, we estimated that the new terminal velocity of such a system is not set by tensile strength, but rather when the leakage radiation equals the incoming radiation energy balance. We estimate that this critical speed would occur at about 1,000 kilometers per second. That is a whopping 100-fold improvement upon what we had before. Now, this still isn't comparable to Starshot's 20% the speed of light, but it's not bad. It's 0.3% the speed of light. Now, the really fun thing about this is that TARS could actually be used here for a completely different purpose. Now, we didn't look at this too closely in the paper. It's definitely an area where I'd want to see more follow-up research. But having said that, TARS is here essentially converting solar energy into a magnetic field, and magnetic fields can be quite useful. For example, one might imagine a Mars base in the near future that would be vulnerable to ionized radiation from the sun, since of course Mars lacks much of a magnetic field itself. So one could then place one or more of these TARS systems in a geostationary Martian orbit that hover over a base and provide a localized magnetic field, protection for the inhabitants. Given their low mass and cost, there's no reason why we couldn't dump many of these in orbit, in fact, and create a whole fleet of them. Now, I could keep going here, as you can probably tell, but at a certain point you have to pause, take a deep breath, and let the world see what you're cooking, because science doesn't happen in a vacuum. It depends on peer review and community feedback. I want to be crystal clear that TARS is not some silver bullet for interstellar travel. It is, at best, only capable of 1,000 kilometers per second, and even then, only for tiny probes. There's no way Cooper is going to be sat inside this thing and surviving the insane G-forces involved. My motivation here, as is true of much of my work, is to take a great idea like Breakthrough Starshot and ask, what does a more realizable version of this look like? Is there some different physics we could exploit to get there, and hopefully to encourage others to do the same? This work was supported by many of you, our Cool Worlds donors, not just in terms of the research itself, such as hiring Catherine to help with those engineering calculations, but also in terms of hiring a team at Caltech to produce many of the spacecraft animations that you've been enjoying throughout this video. So a huge thank you to everyone who made this possible. And if you are watching this and want to support what we are doing here, then you can use the link down below to become a Cool Worlds donor, just like many of our awesome fans out there. If nothing else, I just hope that this video might rekindle within you some of that sea longing, to re-spark your imagination, that maybe together we might be able to figure this out. So Until next time, stay thoughtful and stay curious.
I built this for you. I'm limited by the technology of my time. But one day you'll figure this out. And when you do, you will change the world.